Now, when we can convert a matrix A to a matrix B through similarity transformation, then both matrices A and B share the same certain characteristics. And these characteristics, preserved through similarity transformation, is called similarity invariant. These properties are invariant. Or we can say, in other words, the properties are invariant under similarity transformation. So, what are the similarity invariant properties? They are the determinant of A and the determinant of B through this similarity transformation. That means we have P minus 1 A P equals to B. Then matrices A and matrices B have the same determinant. If A is invertible, then B is also invertible. So you think of this as B. What else? The rank of A is the rank of B. The nullity of A is the nullity of B. Remember, nullity is a number, the dimension of the null space of A. Here is just a number. How many dimension in the null space? So the number of dimension in null space of A is the same as the null space of B. The trace are the same. The characteristic polynomials are the same. Even the eigenvalues are the same. Lastly, the eigenvectors are not the same, but the eigenspace dimension are the same. Okay, so you realize that if we are studying, we have A and we can convert it to B, then B has so much similar properties to A that if B is a very simple matrix, then many things can be reviewed. So the simplest matrix that we can ever find, or one of the simplest, is the diagonal matrix, because a diagonal matrix has very nice way to compute its rank, its invertibility, its determinant, its trace, its eigenvalues. Okay, so why do we like a matrix to be similar to a diagonal matrix? These are the two notes that you can find more details. I have summarized them. The first is that eigenvalues of a diagonal matrix are simply the diagonal elements. We have seen that in the past lecture. The determinant is simply the product of the diagonal entries. So very quickly, we can determine the product. We can determine the determinant value of the matrix. The rank is the number of non-zero entries in the diagonal. You can count very quickly what is the rank of a matrix D. Additionally, the matrix multiplication of A times D and D times A. In here, the A is any matrix, okay? Not the A we are talking about just now. A times D and D times A is when we pre-multiply A by a diagonal matrix D, so that means it's D times A. Then what we are doing is we are multiplying the rows of A with the elements of D. Post-multiply means A times D. This will be useful. The columns of A are multiplied with the diagonal elements of D. Okay, so you'll see that later on. Right, now the diagonal matrix inverse is also very simple. It's simply the reciprocal of the diagonal elements. And if we have diagonal matrices multiplying with each other, especially D times D equals to D square, then it is simply the diagonal elements square. So we also come to that. So we like diagonal matrices very much.